So hello everyone, welcome to this MLSS lecture. We are happy to have Kostis again with us for the second part of his talk on game theory and machine learning. So Kostis, the stage is to you.
Hi, let me share my screen. All right, so I hope you can see that. So I'm going to pick up where I left it last time. So I was talking about game theory and machine learning. Again, it's a great pleasure to be in this exciting summer school. So last time, so what I'm going to do today is I'm going to sort of like remind you the broader context of this talk in case you missed the first lecture, and then I'm going to pick it up from where I left it. The standard machine learning setting thinks of a agent that is consuming data from their environment and learns enough about their environment to make predictions and also make decisions. So in the future, we are expecting that this agent is not going to be by themselves, but they're going to be in an environment that contains other agents, that one or actually multiple other agents. And in such an environment, what is taking place is that you have this interaction between the utilities that these agents have, which drive their decisions, and which in turn influence the state of the world, and which in turn influences the learning experience that these agents have in the system. So I believe that the future of AI will need to develop more tools than the existing tools to understand how multiple agents with utilities interact in a stateful world in which they make decisions and they're learning, and the decisions that they're making affect the state of the world and the learning experience of others. So I think the future of AI will contain the elements of both learning and strategic reasoning. And this is the motivation of these lectures. Last time I gave a few example challenges, and these example challenges were there to motivate what I see as interesting applications that exhibit both of these two components. And again, as I stated last time, these challenges that I mentioned were to be taken metaphorically as examples of settings that involve these two components. In the rest of my lecture last time, though, I focused on a very specific aspect of the types of tools that we need to develop to address that future that contains learning and strategic reasoning, which had to do with optimization. And in the beginning of my lecture last time, I started with a dictum. And that dictum was saying that minimization is to current AI what min-max optimization is to future AI, or more broadly, what multi-agent equilibrium learning is to future AI. And the way I justified this position is that minimization is useful when you're thinking of a learning agent that is learning and making decisions in a stationary environment. By stationary, I don't mean that the environment does not have state. Maybe the environment does have state, but the laws that govern how the environment operates do not change in time, because of the presence of other agents in the system. In turn, when you have multiple agents, you have to be thinking about min-max optimization and equilibrium learning algorithms. And the reason is that these algorithms are applicable when the AI agent is learning and making decisions in a changing environment that might be changing because, as I said earlier, there could be other agents that are learning at the same time and have either conflicting or aligned interests. But the point is that the joint decision making of the agents is affecting the state of the world. And this is sort of like a literal, if you want, application of equilibrium in a learning setting. But there are also other ways in which min-max optimization and equilibrium learning become relevant. And this could happen because it's not the case that you are envisioning other agents interacting with your agent, but you want to make an agent that is robust to all sorts of things. For example, noise in the data or poisoning of data that is used to learn, or the need to enforce constraints on the learning outcomes as it happens in GANs, where, for example, a discriminator agent is there to enforce constraints on the distribution generated by the generator agent. So again, so the focus of my pair of lectures is on a particular aspect of what I envision will be important tools to develop for the future, and that has to do with min-max optimization. So the problem I was talking about last time was the problem min over x in some constraint set, max over y in some constraint set, fxy, where fxy is some function of x and y. I discussed a bit the long history of this problem in mathematics, optimization, game theory, learning, etc. And as I described last time, the best case scenario for this problem is when f is continuous and it is convex in x for all y and concave in y for all x. These types of functions called convex-concave satisfy this beautiful property that min-max of f of xy equals max-min of f of xy under the conditions that are stated for the function, and also that the constraint sets are convex and compact. That is, if you, I mean, so, okay, so closed and bounded. So, moreover, the solutions to the left-hand side here, with respect to x, are a convex set. If the function is strictly convex-concave, it's going to be a unique solution over here. And similarly for this other side. And the game theoretic interpretation of, and the reason why von Neumann's theorem was so important for the foundations of game theory is the following, that if x star is an optimum for the left-hand side over here, and the y star is an optimum for the right-hand side over there, then this pair f x star and y star is an equilibrium of the zero-sum game where there are two players, the min and the max player, and the min player is paying the max player fxy. So the min player wants to minimize that payment, and the y player wants to maximize that payment. As I said, there are intimate connections between this theorem and mathematical programming, as was discovered by von Neumann, Danzig, and others. Equilibrium computation in the setting that I just described, so solving this star, is equivalent to being able to do convex programming. And moreover, as shown by a long sequence of works, if the two players of the game use no-regret learning algorithms to update their strategies in parallel, the resulting trajectories, xt, where xt is the trajectory of the x player, and yt, the trajectory of the y player, converge to a min-max equilibrium of the game. Okay, can I ask you something? Do you see a bar at the bottom of the slide, or you see a clean slide? over here. Is there anything over the equation here?
We see the clean slide.
Okay, nice. Because I do see something, but if you do see it cleanly, that's cool. Okay. So this is all from last time, but min-max optimization has found some exciting applications in machine learning recently. For example, GAN training and training against adversarial attacks. And these types of settings exacerbate the importance of shooting for first order methods because these settings are high dimensional, shooting for last iterate convergence, and taking an interest on non-convex concave objectives. These applications, in fact, emphasize how important optimization is, because without taking care, what you observe is training oscillations. So on the left and on the right, these are graphs I showed you last time. You see training oscillations exhibited by the generator and the discriminator in some simple GAN training scenarios. And indeed, the simplest example where you observe oscillations in min-max optimization is this very trivial function, min over x scalar, max over y scalar, x times y. As I showed last time, and in fact was asked by somebody to, and I provided a proof of that claim, if you do gradient descent for the x player and gradient ascent for the y player in parallel, what you see is that the trajectories of the two agents spiral away from the equilibrium. So in this setting, the equilibrium is the 0,0 point. And if you start gradient descent, ascent dynamics, out of any point, you'll see this spiraling out behavior going away from the equilibrium. So that motivated, I'm still doing my overview from last time. That motivated us last time to think about alternative methods to gradient descent ascent. And I proposed two methods, not mine. These were known in the literature, but I proposed using them to argue, to remove the oscillations. One is called optimistic gradient descent ascent, which finds its roots in Popov's work from 1980. And the other one is extra gradient method, which finds its roots in Korpelevich's work in 1976. OGDA has a clear interpretation as a negative momentum method because you do the normal gradient updates, except you undo some of the gradient that you asked in the previous round. So for the min player, you add a little bit of yesterday's gradient. For the max player, you subtract a little bit of yesterday's gradient. So you undo a little bit of the gradients of the previous step. Extra gradient is a bit tougher to interpret as a gradient, negative gradient method, but the dynamics are written here. Let me not dwell so much into that, as I talked about it last time. But the sort of like the conclusion from last time is that OGDA and EG with constant step size exhibit last iterate convergence to the min-max equilibrium as long as you have a smooth convex and concave function fxy. And also convergence rates are known mostly for the unconstrained setting. So in the convex-concave domain, there are interesting open problems remaining that have to do with understanding rates of last iterate convergence for constraint problems. And this concludes my overview from last time. I just wanted to anchor our conversation for today to where we left it last time. So in particular, what I did today is I overviewed the first part of my pair of lectures, which focused on the convex-concave domain. And the goal of today's lecture is to focus on the non-convex, non-concave setting. So what I'd like to do is I'd like to first fool around a little bit with that setting. Second, take a step back and think about what is an interesting even target in when you have non-convexity and non-concavity in your objective. And then I'm going to look into the computational complexity of computing these types of solutions. All right, so let me start. Unless there are any questions from sort of like pertaining to my previous lecture, I will proceed with the new stuff. Cool. So first of all, let's ignore the question of, like what we're really shooting for, and ask the question, okay, like if we were to use negative momentum in the wild, that is outside of the convex-concave setting, what's going to happen? Are we going to see any improvement in removing oscillations? So in some work a couple of years ago, where we sort of like started looking at OGDA, optimistic gradient descent ascent, we also proposed a adaptation of the standard Adam algorithm, an adaptation with negative momentum that we called optimistic Adam. So as you know, I'm sure you might have used the algorithm yourselves. Adam is a variant of gradient descent ascent that works very well in practice, and it has a momentum component as well as a parameter adaptive per parameter adaptive learning rates. So the method is widely used, even though it actually has been shown to fail to converge, even in reasonably behaved settings. So in any event, so optimistic Adam is the right adaptation of Adam that similarly to OGDA undoes some of the past gradients. So it has some negative momentum. So what we did, and these are sort of like plots from like a few years ago, but just to try to test the hypothesis that negative momentum might be useful. What we did is we took the same data set, we took CFAR 10, and we used the same hyperparameter, the same GAN architecture and same hyperparameters as the paper of Gururajan et al. from that year. And what we did is we tried 4 optimization algorithms for that are to be used by the min and max players in the GAN formulation. So it's okay. So these are the 4 curves that you see here. Let me explain what they represent. So there are 2 simulations where we used the Adam algorithm for both the min and the max player, and there are 2 simulations where we used optimistic Adam for both players of the min-max problem. So for both the generator and the discriminator. So for each algorithm, we are interested in what happens as follows. So what we did is we tried using Adam, where the generator does 1 step. So the discriminator, the inner player, does, let's say, several steps for every, actually 5 steps for every step of the outer player of the generator, versus a 1-1 ratio. So the green curve is when you do Adam, one step, 1 step. The blue curve is when you do Adam, but 5 steps for the inner player, 1 step for the outer player. Similarly, the purple curve is when you do optimistic Adam, 1 step per player. The red curve is when you do optimistic 1 versus 5 steps of optimistic Adam. And you have this interesting behavior that, first of all, optimistic Adam beats with a 1-to-1 ratio as predicted by theory, right? So theory wants to do 1-and-1 ratio. As predicted by theory, optimistic Adam beats the other algorithms. That's an interesting takeaway. The other interesting takeaway is that Adam itself, which is a gradient, and a gradient method without negative momentum, actually benefits from having different ratios in the number of steps. Right, so that's an interesting takeaway, right? So I showed you some plots last time where I did argue that it's actually useful to have the inner player, the max player, do several steps for every step of the outer player, because effectively what that does is it effectively tries to compute the max fxy function for a given choice of the x player. So it does make sense, and I showed you even in my simpler simulations last time that doing different number of steps for the two players does decrease at least the oscillations. So indeed, as expected over here as well, Adam with 1 versus 5 steps does better than Adam with 1 versus 1 step. On the other hand, when you go to the optimistic world, well, the optimistic, the negative momentum was motivated exactly by this, to avoid trying to play these kinds of tricks. And it is, as shown in this picture, optimistic Adam does not need a different number of steps. So that's one takeaway. Yeah, so I guess here I do some, for a smaller number of epochs, I also put some error bars to show that, it's not just, like my simulations that it's not sort of like just some noisy simulations that ended up being away from each other. It's just that I also give you some error bars here. And again, these are all simulations, but the point is that the benefits of negative momentum have also been explored by other works. And there seems to be enough supporting evidence that negative momentum might be a good practical advice when you solve min-max optimization problems. So if you encounter min-max problems, it might be a reasonable idea to try using negative momentum. And here's also another funny plot from Gidel et al. That supports this idea as well. So here, what the authors plot is for various papers that train GANs, how they set the momentum of the Adam algorithm that they use. And at the time of writing of that paper, which was like a couple of years ago now, I guess, you see this decreasing monotonically with time, decreasing as like people get better and better GANs. They also, you get this trend that, if you look at their experiments, you get this trend of decreasing and decreasing the momentum that they use in the Adam algorithm, okay? So at the time of writing, they had reached 0. So, but, I guess what I'm advocating is using negative momentum as a interesting, as a potentially useful practical advice. Is there a question here in the chat?
There's one question. The question is, was the effect, I think it's 2 slides back, where you showed the 4 different traces.
Yes, right. So is the effect, have we tried it more broadly to different data sets? We did not. We tried CIFAR10. And we also, of course, like in that paper, I also showed you, like for the Gaussian example, how last time, how oscillations are removed by optimistic methods. But follow-up work has tried it on other data sets. So they have done more complete comparisons to other data sets. I am not a practitioner enough to give you like better evidence, but this has been explored, and indeed, if you find yourself in a situation where this method helps you, please let me know, because it will be interesting for me to know. All right, so this is sort of like some trying things out type of approach. But now, as I said, I want to take a step back, and I want to be thinking, okay, like if you are in a non convex-concave setting, what should even be the goal of your optimization? Okay, and of course, as I pointed last time, if f fails to be convex-concave, then von Neumann's theorem breaks. So what does that mean? It means that for some functions, the min-max could be different than the max-min. For some other functions, equality may hold, but there could be multiple disconnected solutions. And again, sort of like currently I'm thinking about x's that are compact and convex. So the min-max and the max-min are actually well-defined. But like what breaks is not that they're not well-defined, but the equality or the multiplicity and disconnectedness of solutions. So I gave two examples last time. So this function here fails to be convex in x, while it is concave in y. And the result is that you get two solutions. And they are disconnected. This function here, and again, so I'm optimizing this over plus minus 1 and this over plus minus 1. This function here, the left-hand side and the right-hand side are different. So I believe you solve this, you get 0. Because for every choice of y, min player goes and sets x equals to y. So this inner function here is a 0 function. So the thing is 0. This one is a bit more complex, but I believe if you do it, you get 1 over here. So 1 is different than 0, of course. So, and here what failed is that you are convex in x, but you're not concave in y. And these are just some trivial examples. Imagine what happens for more complex functions. All right, so in the absence of sort of like a clear theory telling us what to do, the question is, what should even be the goal in min-max optimization when the objective is not convex-concave? And since we're talking about general settings, I want to make it even more general, okay? So what I'm going to consider is the following problem. You have a continuous function f, no assumption about its convexity or concavity in the two variables, x and y. You're also given a constraint set S. So what you want to do is you want to solve a min-max problem subject to the constraint that you have to respect the constraint set S. And what I want to describe is I want to describe a few solution concepts that have been recently proposed in the literature as people have been trying to think what are reasonable solutions to go after in the absence of convex concavity of the function f. So I think this slide is going to be slightly notation heavy, so I'm sorry about that. But hopefully it's going to be the only slide that is a bit notation heavy. And the reason it's notation heavy is because I was shooting for a very general setting, and notation actually, as I was making the slide, did become a bit heavy. To explain the slide, I want to make a couple definitions. So I'm going to be calling for a given little x, s of x c dot are going to be all y's such that the result xy belongs in my constraint set. So it's kind of like it's the conditional of this set if we set this x guy, x coordinate. S subscript capital X are all the x's for which there exists some y so that they are in the set S. These two are two different things. This is just the, let's say, the marginal, let's say, of this set on the x variables. And this is the conditional of the set S, if I may use this term, if you set the x variable to this little x. And I'll similarly define, like the conditional on y and the marginal on the y variables. Okay, on the y variable. So okay, so please keep that notation in mind. And here are some definitions that are reasonable and have been proposed in the literature for this problem. So the first solution, which is probably the most natural, is the local mean global max solution to the problem. What does that mean? So that means that I want you to come up with a point x star y star that respects my constraints and also satisfies the following properties. So the function value at x star y star cannot be cannot be increased by changing y star to anything that is compatible with x star. So the y player, given x star, the y player is doing the optimal thing they could do without violating the constraints. This is the first inequality. That's what it means. At x star y star, the inner player who's maximizing cannot change to make the function larger. So it is globally optimal with respect to the y player. And what the right-hand side says is that it's also locally optimal with respect to the outside player. Again, you know, I didn't want to go for like global min, global max, because of course that's going to be intractable. So the first relaxation to global min, global max type of constraint is to have the inner player be at the max and have the outer player be at a local max, local mean. So let's see if this is really capturing local mean for the x player. This is a bit complex. So let's see. So what's happening here? So we're thinking of x switching from x star to some other x. I want that move to be local. So I want to constrain x to be in a neighborhood, in a delta neighborhood of x star. So I want local optimality with respect to x. So I don't want x to go too far away from x star. Of course, it couldn't go outside of what is permitted by the constraint set. Okay, so it has to be local and it has to be allowed. And after x considers this little jiggling of his x, now the inner player is a max player, right? So the min player is thinking that, okay, if I jiggle, then the max player is going to respond. And the max player, because you know, we don't make any so we want the max player to be doing global optimizations. Once the x player goes to little x, the y player is just going to maximize. So we want that the result of this procedure, we don't want that to be able to decrease the function value. So the min player is thinking, okay, if I jiggle my x star to something else and I anticipate the response of the y player, that is only going to hurt me because I'm a minimizing player. So this is what is captured by this inequality. So x star, y star is a local mean global max solution if neither of the two players can jiggle, neither of the two players can change their points to improve their position. So the inner player is considering global changes of its y variable, and those global changes cannot increase the function value. The outer player is thinking about jiggling locally x, and we want that their anticipated payment, if y best responds, is not smaller than what they're currently getting x star or y star. This is what the solution is trying to capture. And the reason of this asymmetry between the one player and the other is because of I'm doing a min-max problem, right? So a min-max problem, so this concept here is trying to capture the sequentiality, the sequential nature of the optimization problem. This is the motivation for this first definition. So this is a definition that tries to capture the sequential nature of min max of fxy. If I was looking at max min, the positions of the players would be reversed. So max player is anticipating while min player is just doing best response. So this is the motivation for this first take on the problem. The second approach proposed by Jean Trapali and Jordan in a recent paper is a local version of that previous solution where, again, in take one, X was jiggling, Y was doing global moves. In this local minimax solution proposed by Jean et al., also the Y jiggles. So Y is not making huge moves anymore. Both X jiggles and Y jiggles. So Y jiggles myopically. X jiggles anticipating the changes that this may cause to the Y player. So it's a local version of take one. And again, both these concepts are asymmetric with respect to the roles of min and max because they are shooting for solutions that capture the sequential nature of this definition. For whatever applications, a sequential interpretation of this is reasonable. In a paper with Panageas and a parallel work of Mazudmar and Ratliff, we proposed a parallel move, local min-max solution, and we call it the local min-max equilibrium to kind of like point to the fact that we're looking at equilibria when people make actions, choose actions in parallel. So what we want is that the natural thing that a point x star that is y star that is feasible, and such that neither y can jiggle to improve the payment that they receive from the x player, nor x. Sorry, I said the other way around. No, neither y can jiggle to increase their payment. So any jiggling results in smaller payments, nor x can jiggle to decrease the payment that they're making to the other guy. Okay, and I'm talking about jiggling because I'm looking at local moves. Right, so x is choosing something in the neighborhood of x star as long as it's compatible with y star, and y is choosing something in the neighborhood of y star as long as it's compatible with x star. So as I emphasized, 1 and 2 take a sequential interpretation of this problem, useful in some applications. Take 3 takes a simultaneous move interpretation of what this problem means, and which is useful in some applications. So the first is guaranteed to exist, but it's NP hard to compute because the Y player is doing global optimization. 2 and 3 may not actually exist for every f. So, right, so to relate these concepts in fact, so 1 always exists, but it's hard to find, NP hard. 2 and 3 are local, so it's not obvious that they're hard, but they may not exist. So they're not guaranteed. They're not sort of like solutions that, similar to min-max equilibrium in convex-concave domains or Nash equilibrium in general games. They're guaranteed to exist. We also have the following nested property that local min-max equilibria, when they exist, they are contained in the set of local minimax solutions. And the reason is that, again, that, like local minimax solutions are thinking of it as a two-stage game where the outer player is thinking in anticipation of the actions of the inner player. So it's a stronger, as it turns out, if you satisfy these constraints, you have to belong in this bigger set. Also, local min-max equilibria are contained in the set of fixed points of the gradient descent ascent algorithm. So remember that gradient descent ascent, so these classical algorithms to solve min-max problems, takes this form where I also have a projection on the constraint set to satisfy those constraints. So at every step, I take a gradient step for x, a gradient step for y, and then I project to the constraint set. So these are my gradient descent ascent dynamics. So sort of like another reasonable solution concept for this problem is, arrive at a point where gradient descent ascent wouldn't be able to improve you. So as it turns out, the fixed points of this operator, the GDA operator, contain local min-max equilibria, but maybe not necessarily contain local min-max solutions. So these are sort of like concepts that are well motivated and are local. They are local. But as I said, this orange and yellow sets might be empty, unfortunately. On the other hand, and this is the motivation, like for this thinking about fixed points of GDA, they're actually guaranteed not to be empty if your function f is continuously differentiable. And the reason this is true is by Brauer's fixed point theorem. So this operator here, because this set S is compact, I forgot to say it, and convex, and because the gradients, if the gradients are continuously differentiable, then this operator is a continuous mapping from S to itself, and Brauer's fixed point theorem guarantees that the fixed point exists. So here we get the guaranteed existence of solutions by Brauer's fixed point theorem, and sort of like this red oval is guaranteed to be non-empty no matter what f and s are. So that is maybe an argument for thinking of fixed points of the GDA procedure as reasonable targets in min-max problems where the function f is not convex-concave. And sort of like, fixed points of GDA are effectively capturing first order min-max, first order local min-max solutions. Because sort of like for this to be stable, either you're inside the constraint set and your gradients are zero, so you cannot improve your position, or you are on the boundary and the gradient cannot, like the gradient, descent for the x player is pushing you outside of the constraint set, and ascent for the y player is pushing you outside. So it is a reasonable first order type of solution to this problem, and it has guaranteed solutions, so it is attractive from the perspective of a target for optimization algorithms, right? Because in general, what does it mean? Like, so, what does it mean to be looking for something that may not exist? So ideally, you'd like some conditions under which what you're looking for is guaranteed to exist. And over here, we don't need to make any conditions because this always exists. So that's why I find it attractive to be thinking about these first order stationary points. You can start thinking about also second order stationary points and so on and so forth by looking at fixed points of like higher order methods. And again, like Brauer's fixed point theorem, under the right continuity assumptions would also allow you to get some guaranteed existence. So I feel like over here, when, in the lack of convexity and concavity, it is very reasonable to be thinking about first or second order fixed points of a procedure like this as reasonable candidates for what you should be looking for in this setting. One sort of like unclear thing here is like, why, what causes this discrepancy? Why is this yellow thing bigger than why is this red thing bigger than the yellow set? I mean, local min-max solutions are really x points that cannot be jiggled to improve. GDA effectively is capturing that, things that cannot be jiggled to improve. So how come the set red is bigger than the set yellow? That's sort of like an interesting thing, right? Why does that happen? And a possible sort of like point of discrepancy is that it could be that GDA has some fixed points that are unstable and which are not locally minimax solutions. So maybe the discrepancy between the red and the yellow is due to some so GDA allowing some fixed points that are unstable and they are not local min-max solutions. So I guess what I want to discuss a little bit is this discrepancy caused by GDA permitting unstable solutions while local min-max points being always sort of like just the stable points of GDA. And I want to argue that this is not the case. So first of all, it is not the case that min-max solutions are stable necessarily for GDA. And you've already seen the example, right? So if I take the function x times y, the point 0, 0 is a min-max solution. But if I start my GDA dynamics at any point that is not equal to 0, 0, as I argued, it's going to be spiraling away. So this 0, 0 point is a local min-max solution. Neither x nor y can jiggle to improve their position, but it is not stable for the GDA dynamics. Okay, so it's so local min-max may actually have contain unstable fixed points for GDA. So they're not only local min-max solutions are not necessarily stable for GDA. That's the first point I want to make. The second point I want to make is that even the stable points of GDA can be a strict superset of the local min-max equilibria. So there are stable points of GDA that actually are not locally minimax. And this is a simple example that shows that. So this function here, as you see, is not convex-concave. It's concave in both x and y. And in particular, the point 0 is not a locally minimax solution. Over here in this plot, I hope you can make it. I don't know if I can zoom. I guess I don't know how to zoom, but no, I don't know how to zoom. But I'm showing you also the gradient field of the GDA dynamic. So the point 0, 0 is not a local min-max solution for this function. Yet, I want to claim that it is stable for the gradient descent-ascent dynamic. And basically what happens is that at 0, 0, the minimizing player has an incentive to move away from 0. So go either left or right, because of course, he's looking at a quadratic, okay? So he wants to go, but the moment he goes away, that gives an incentive to the y player to either to push to the diagonal, which will actually push both players back to the 0 point. So even though x is trying to escape, because he's looking at a concave function, right? Nevertheless, the moment he tries to escape, both come back to 0. So it's a stable point for GDA, but it's not a local min-max solution. So you get these interesting effects of interacting second order and first order properties of the function f. On the other hand, you can show the following. You can show that the containment, so you get this containment that local min-max, strongly local min-max. So in particular, if you get rid of this issue here, by assuming that your min-max solution is strongly is strongly local min and strongly local max. So the Hessian with respect to x is bounded away from 0, and the Hessian with respect to y is bounded away from 0, all singular, all eigenvalues. You get this containment that all such local min-max are stable points of GDA. And also in that paper, we consider also OGDA, and you get this nestedness that OGDA permits more stable points than GDA, and GDA permits more stable points, as shown in this example, than just purely local min-max solutions. So these are sort of like, you know, like a slide sort of like trying to explain the discrepancy between fixed points of this gradient descent ascent field, which is a first order method, and the notion of local min-max solutions, equilibria. So for the next part of my talk, I would like to address, okay, so now sort of like I explained what these things mean. I also talked about this inclusion and also played around with stable solutions, stability. Now I want to focus on this red blob that is guaranteed to always contain solutions, no matter what F is and S are. And I want to understand the computational complexity of finding fixed points of that, of GDA. Okay, so from now on, I'm focusing on fixed points of GDA as a reasonable solution concept. And I want to describe the computational aspects of computing such fixed points. Maybe there are questions. If there are questions, maybe I can stop for some.
There was one question, but it was answered already. So
okay,
so we can continue, I think.
Okay, great. Okay, and what I'm about to describe to you are some beautiful results from complexity theory and topology. And I'm going to do a small little course in fixed point complexity. So I'm not going to say something too advanced, but I hope that what I'm about to present is beautiful and you know, like of the type that you know you would like to describe to your friends in a dinner conversation and stuff like that. Okay, so let me do that. All right, so from now on, from the next segment of my talk, our target is to compute fixed points of the gradient descent ascent dynamic, which are first order local min-max solutions. In particular, given some epsilon, which is the approximation guarantee, and neta, the learning rate in here, also given access to a function f and its gradient, you know, think of it as having first order access to f. Also given a projection algorithm to the set S, which recall is a convex and compact set, your goal is to find a point x star y star that is almost fixed by the FGDA, by this mapping, the mapping in gradient descent ascent. So that is the goal. So the goal is to find an approximate fixed point of the gradient descent ascent dynamic. So if f is an arbitrary function, this seems pretty hard, okay? But what I want to ask is, but is it NP hard? Okay, it's hard, but is it NP hard? That's my question. And my answer is it's not NP hard unless NP equals co-NP, which is a complexity theoretic collapse that people do not believe. And the reason that this problem, as stated, is not NP hard is because a solution always exists, as we argued earlier, by Brouwer's fixed point theorem. So typically, NP hard problems draw their complexity from the possibility that a solution doesn't exist. But over here, a solution is guaranteed to exist. And the way we prove that a solution is guaranteed to exist is we use Brouwer's fixed point theorem. And finding approximate Brouwer fixed points is known to be lower than NP complete problems. Like finding fixed points of Brouwer functions is an easier problem than NP complete problems. Again, unless some complexity theoretic collapse that people don't expect happens So the class, there is a in particular, there's a complexity class that's called PPAD that I'm going to explain in a little bit, that lies between the hardest problems in NP and above polynomial time, that captures exactly computing. So this arrow is supposed to go to PPAD, okay? That captures exactly the complexity of computing Brouwer fixed points, and also the complexity of finding Nash equilibria in non-zero sum games. Okay, so that means that there is a class that is below NP completeness that exactly captures how hard it is to compute Brouwer fixed points and Nash equilibria in non-zero sum games. And because the existence of GDA fixed points was obtained using Brouwer's fixed point theorem, this implies that the computational complexity of finding GDA fixed points cannot be higher than PPAD. So it must be somewhere between this class PPAD and the class polynomial time. Okay? And what I would like to explore is what PPAD means now and what is the real complexity of the problem that we're interested in. And this is where the beautiful thing begins, okay? So PPAD is a complexity class. I hope you guys have taken a class in complexity theory, but complexity classes are about Turing machines and circuits and discrete combinatorial problems. On the other hand, PPAD aims to capture continuous problems like finding Nash equilibria in general sum games and computing Brouwer fixed points, which are not combinatorial problems, at least a priori. So how do you make the bridge between combinatorial optimization and these continuous problems? This is the goal of PPAD, and PPAD has a combinatorial definition that I'm about to give. So PPAD is the class of all problems in NP that always have a solution, and the reason, the argument that proves the existence of a solution is a very simple statement, which is a parity argument on directed graphs that states that if a directed graph has an unbalanced node, which is a node that has different in degree and out degree, it must have another unbalanced node. I hope you all know or find this statement trivial, right? So if I give you any directed graph that is finite, if there is a node whose in degree is different than the out degree, then there must be another node that has different in and out degree, because the sum of in degrees and out degrees, the sum of the in degrees is equal to the sum of the out degrees of nodes in a graph that is finite. And as such, if a node is unbalanced, there must be another one that is unbalanced. So PPAD is the class of all problems in NP that are guaranteed to have a solution. And the reason that they are guaranteed to have a solution is this trivial statement. Okay. Now, what does this have to do with fixed points? So that's the real question. Okay. And my claim is that if you read Brouwer's theorem, the proof of Brouwer's theorem, there is a lot of math that is continuous math. But at some point, a miracle happens that guarantees the existence of a solution. And then, there's more continuous math. And I claim that if you look at what happens here, what is really like in the core, like if you strip away all the setting and all the continuous math around the proof of Brouwer's fixed point theorem, and you look at what happens here in the core, in the heart of the argument that guarantees the existence of Brouwer's fixed points, actually, surprisingly, you get this trivial parity argument in directed graphs. So this is beautiful and surprising. So what I'm telling you is that these things you learned in topology, these amazing existence theorems that have all these corollaries. Okay, so Brouwer's fixed point theorem has a lot of corollaries, including the existence of Nash equilibria in general sum games as proven by Nash. The existence of GDA fixed points that we argued here, but and a ton of other things. So the surprising fact is that in the heart of this amazing theorem, after you strip away all the details, this is the core, this is the real thing that is happening there. That the existence of Brauer fixed points boils down to this trivial graph theoretic lemma that we learned in our first combinatorics class. So that's pretty beautiful and surprising. And what I'd like to do is I'd like to give you a hint for why this parity argument actually is relevant in arguing the existence of fixed points. And to do so, I'm going to prove to you a very cute lemma, and this is the dinner party conversation, that is called Sperner's lemma. And Sperner's lemma lies in the heart of proving Brauer's fixed point theorem, or at least Brauer's fixed point theorem can be proven using this lemma. All right. So Sperner's lemma states the following: take a two-dimensional grid, triangulated, as shown in the figure, and color the boundary with three colors in the precise way that I'm showing you here. In particular, this edge is called red, but this node. These two edges are called blue, but this node, and this edge is colored yellow, but this node. Okay, so fix this precise boundary coloring. So Sperner's lemma says you're free to color the internal nodes in whatever way you want using these three colors. No matter how you color the internal nodes, there will exist at least one triangle that has all three colors. There's no way to avoid a triangle that has all three colors if you respect this boundary coloring and color the inside in whatever way you want. So I hope you can spot some of the trichromatic triangles here. In fact, there is an odd number of them, also follows by Sperner's lemma. Here are the 5, in this case, trichromatic triangles. Okay, different colorings will induce different numbers of trichromatic triangles, but there's always going to be an odd number. So in particular, at least one. Okay, that's the claim. So what I would like to do is I would like to actually prove to you the theorem. I would prove to you this cute combinatorial fact that, as I said, lies in the heart of proving Brauer's fixed point theorem. And I claim that kind of like as I'm doing my proof, this parity argument in directed graphs will show up. After I do that, that will motivate my definition of PPAD class, and then I'll move on to the complexity of GDA fixed points. But for now, let's think about this nice dinner conversation type of question. Okay, so I want to prove that there is a trichromatic triangle. So let me forget their existence or where they are. And what I'm going to do is I'm going to define a walk in this square. So what I'm going to do is I'm going to envision this square as being a factory that has triangular rooms. And I'm going to start my walk in this factory starting from the bottom left triangle. Notice that this triangle, the three pillars of that room are all on the boundary of the square. You colored the internal vertices, so you have no control as to the colors of the three pillars of my starting room. So in particular, no matter how you color the internal nodes, the three pillars of my starting room will look exactly like in this picture. In particular, that triangular room where I start has exactly 2 red-yellow doors, and it has exactly 1 red-yellow door that I can cross with yellow on my left-hand side. So what I'm going to do is to cross that door that is a red-yellow door and has yellow on my left-hand side. So if I cross that door, I enter into a new room. So that room, I entered into that room through a red-yellow door. So certainly that room has 2 of the 3 colors. The question is, what is the other pillar? So I enter into a room through a red yellow door. If the other pillar is blue, well, I found my trichromatic triangle because I entered through a red yellow door and the other pillar was blue. If the other pillar is not blue, so it's either red or it is yellow, I claim that will have to then open up another red yellow door for me to cross with yellow on my left. In this case, you decided to color this pillar to be yellow. So I entered into this room through a red yellow door, and the other pillar that I saw was yellow. And that opened this red yellow door for me to cross, having yellow on my left, which is what I'm going to do. And I'm going to repeat this as long as I can. So I entered into this room, found another red yellow door, crossed it, another red yellow door, crossed it. You know, all the rooms I encounter, I enter through a red yellow door. So I claim that, you know, if the other pillar isn't blue, there has to be another red yellow door for me to cross with yellow on my left. So this is what I'm doing, okay? So I'm crossing red yellow doors, and surprise, surprise, I have to arrive at a trichromatic triangle. I claim that this is a proof that a trichromatic triangle exists. It's not yet complete, okay? So the idea though is the following, that as I'm moving along in this factory, I go from room to room, crossing red yellow doors. And as I said, you know, like unless the other pillar that I encounter after I cross a red yellow door is blue, I can keep going, okay? Whether it's red or it's yellow, that will open another door for me to cross. So the only way for me to stop is to actually encounter a blue pillar, in which case I stop because I have no red yellow door to cross, but also because I found my trichromatic triangle. The only way my proof can break is, there are two ways it can break. It can break because, you know, I wander in my room and then I hit the boundary and exit the factory. But I claim that this cannot happen because if you look at the boundary, there is no red yellow door you can cross having yellow on your left. There's only, because the boundary coloring is fixed, you cannot influence that with your coloring of the internal nodes. And if you look at all doors in the boundary, there is a unique red yellow door, but crossing it, you have to have yellow on your right. My walk always has yellow on the left when it's crossing red yellow doors. So this cannot happen. So I'll never leave this factory. I have to stay inside. The only stopping condition is if I cross a red yellow door and I found a blue. That's the only stopping condition. So the only way, so there's a finite number of rooms. I cannot escape the factory. My only stopping condition is I enter through a red yellow door and I find a blue. The only way I can possibly fail is if I sort of like wander in the factory and kind of like close a loop and move around the loop forever. So creating a row shape. But I claim that this cannot happen because for you to create a row shape, you need a triangle that has 3 red yellow doors. And you cannot create a triangle with 3 red yellow doors. So you cannot, this path leaving here cannot create a row shape. It cannot exit the factory. And the only stopping condition is to find a blue pillar after crossing a red yellow door. So it has to stop and it will conclude at a trichromatic triangle. So this is a proof of Sperner's lemma. So I argued that at least one trichromatic triangle exists. Let me now try to argue that actually there is an odd number of trichromatic triangles, okay? So after I conclude my first trip that got me to a trichromatic triangle, I'll do the following mental experiment. I will go to another triangle that I haven't visited yet, okay? If that triangle has a red yellow door for me to cross, keeping yellow on my left, I'll do that. That takes me to another trichromatic triangle. I will also do it backwards, okay? So I'm here, I could also be going backwards, having yellow on my left-hand side always. That gave me another triangle. Okay, so I got a path whose both endpoints are trichromatic triangles. I can start somewhere else. For example, I can start over here. There are some triangles that have red yellow doors. Oh, I actually started here. I got another path, both of whose endpoints are trichromatic triangles. Over here, I'm going to cycle, and all the other triangles in this graph do not have red yellow doors. So if I start there, I stay there. So as you see here, all my trichromatic triangles were discovered. And I managed to cover my factory with cycles, paths, whose endpoints are trichromatic, except for this first path, one of whose endpoints was this starting factory. Okay, if I go backwards from here with yellow on my left, I exit the factory. So what the heck happened in this proof, right? Let's abstract away what we did. So the only thing I actually did, the only smart thing I did is I defined a transition rule that goes from a triangle to an adjacent triangle. And that transition rule was if those two triangles share a red-yellow door that I can cross to go from 1 to 2, having yellow on my left, I do that. That's the only thing I did. That's the only thing I defined. This is the only smart thing I did. And the point is that if you define this connectivity structure between triangles in your factory, every triangle actually can have at most one forward neighbor and at most one backward neighbor, because no matter how you color a triangle, it can have at most one red yellow door that you can cross going forward, and at most one red yellow door you can cross going backward. So if I connect triangles according to this rule, every triangle will have at most one out degree at most 1 and in degree at most 1. Moreover, there was a standard triangle that was not influenced by your coloring that actually did have a red yellow door. And following that, the graph starting at the triangle got me to a trichromatic triangle. And everything else was either a cycle or an isolated triangle that had, these are triangles that had no red yellow doors. These are triangles that had red yellow doors, but if you followed that graph, you got into a cycle. And these were others, some paths with paired endpoints that were both trichromatic triangles. So my point is that the proof of Sperner's lemma boils down to a directed parity argument. I defined a directed graph that has in degree and out degree at most 1, and was such that if your out degree is 0 and your in degree is 1, you have to be trichromatic. If your out degree is 1 and your in degree is 0, you have to be trichromatic, unless you are this guy. And all other points that either have 0 in and out degree or equal in and out degree are not trichromatic. So I defined a graph on the space of triangles with the interesting property that it has in and out degree at most 1. So in particular, it comprises paths, cycles, and isolated vertices. And it was also such that any unbalanced node in this graph was a trichromatic triangle, except for this guy, the starting triangle over here. So in particular, because endpoints of paths are paired, go in pairs, and because all those endpoints are valid except this guy, there must be an odd number of trichromatic triangles. So that is the proof of Sperner's lemma. And this is the reason why it boils down to this directed parity argument. Okay, so hopefully PPAD makes sense now. So PPAD is the class of all problems which, like Sperner, always have a solution. And the reason they have a solution is this parity argument. Now, in particular, these problems define implicitly or explicitly a directed graph that has an obvious unbalanced node. In the Sperner case, it was the bottom left triangle, the obvious starting point node. And what they require you to do is to find another unbalanced node. Simple stuff. So Sperner is such a problem, as I argued. Now, because Brouwer can be proven by Sperner, Brouwer is also such a problem. Because Nash can be proven by Brouwer, it's also such a problem. Because fixed points of GDA can be proven by Brouwer, which can be proven by Sperner, they're also such a problem. So all these problems in their heart of the existence argument, they have this nice parity argument. Now, I don't want to confuse you, right? So we do graph algorithms in the first algorithms class. And things with graphs are easy, okay? So like if I give you a graph and I give you an unbalanced node, it's easy to find another node, right? You just inspect all the nodes until you find some node that is unbalanced. So why the heck are these problems hard? I mean, finding an unbalanced node in a graph is not a hard task. You just inspect all of them. And the reason the problem might be hard is that in many problems, you actually can implicitly define an exponentially large graph. So here is why Sperner might be tough, okay? So consider a square that is not n by n, but is 2n, 2 to the n by 2 to the n. And suppose that I gave you oracle access to some circuit that gets as input n bits and another n bits and outputs the color of the node indexed by x and y. This circuit defines, so it takes as a, it's a poly n circuit maybe, but it defines a 2 to the n by 2 to the n, the coloring of a 2 to the n by 2 to the n grid. So in particular, that grid, the number of triangles it contains is exponentially large compared to the description of the circuit. So you get a situation where the graph is implicitly defined by the circuit, but the graph is exponentially larger than the circuit. And this is why the problem is hard. So to solve the Sperner problem, you can indeed, like run this algorithm in a lazy way, evaluating the circuit only as you need it, right? So like you start at the bottom left triangle and start crossing red, yellow doors, only querying the triangles that are relevant, right? But as far as you can tell, this may, this thing may wander in an exponentially large graph, and it could take exponential time to converge. And this is why Sperner is a difficult problem. Sperner is a difficult problem because it defines implicitly a huge graph on which you have to find unbalanced nodes. And this is really the point of PPAD and why it's not a trivial class that belongs to P. Many of these problems, Sperner, Brouwer, Nass, etc., the types of graphs they define are exponentially large. So PPAD lies, as far as we can tell, unless things collapse, between P and NP complete. And it's known to contain very interesting problems that are exactly as hard as this class. So this class, in a similar way that NP completeness captures exactly the complexity of satisfiability and other important problems, PPAD captures exactly Sperner and Brouwer, and as I showed in some work I did a decade ago, Nash equilibrium as well. Okay, so these problems are complete for this class PPAD. Okay, this class is a combinatorial class, but it captures exactly the complexity of these problems. So these problems are both solvable, that is, by running this parity argument, but they're also at least as hard as any other problem in this class. Okay, so now let's go back to the GDA fixed point problem, which is, as far as we can tell, inside PPAD because it reduces to Brouwer, but potentially could be in P. So given some learning rate and some epsilon accuracy and first order access to some function f and its gradient as well, the goal is to compute an approximate fixed point for the GDA dynamics. In recent work, we showed that solving this problem is as hard as all the other problems I was talking about. So even though a priori, this problem could be easier than Brouwer, it's actually exactly as hard as Brouwer. Even though this problem tries to compute equilibria in zero-sum games, it's exactly as hard as finding equilibria in general-sum games. And in particular, it's exactly as hard, it's complete for this class, so exactly as hard as any other problem in this class. So the interpretation is that computing local min-max equilibria and zero-sum games that are not convex-concave is exactly as hard as computing Nash equilibrium in general sum games. So you get no discounts if you consider general functions f. So far I talked about complexity theory and the complexity of fixed points and how that can address the complexity of finding local min-max solutions of functions that are not convex-concave. An interesting corollary, if you're an optimizer who doesn't care about complexity theory, an interesting corollary of our proof is the following: that if you're given oracle access to a Lipschitz smooth function and its gradient, then this is an unconditional result that has nothing to do with complexity theory. It's a result in the oracle model. Given oracle access to a function and its gradient, and even if the function is Lipschitz and smooth, if you want to find an epsilon approximate fixed point of GDA, then you need to make exponentially many queries to f or its gradient. So the queries must be exponential either in one of the following parameters, either the 1 over epsilon, the accuracy, or the Lipschitzness, or the smoothness, or the dimension. So you cannot escape from paying exponential number of queries with respect to at least one of these aspects of your model, of your problem. And again, of course, finding second order local min-max equilibria is going to be tougher than this because they're contained in this first order local min-max. The proof is difficult, okay, to give in a short presentation, but the very rough idea of the proof is that because Sperner is hard for PPAD, so it's PPAD hard, what you want to do is you want to define a function fxy in which the x player is choosing a triangle. So this is what we do. So we define a game where x player chooses a triangle and y player chooses an edge of the triangle chosen by x. And how much the x player is paying the y player depends on a few things. One, whether the triangle chosen by the x player contains a red-yellow edge. Two, whether the y player chose one of these red-yellow edges if they exist. And three, the orientation of the red-yellow edge within the triangle that was chosen by the x player. So what you do is you create a situation where the best response dynamics of the function is following these paths of our proof of the Sperner lemma. And the reason why min-max optimization of fxy can capture this problem is because actually this function fxy can be computed locally with oracle access to the circuit that defines the Sperner instance. If you try to implement this idea with a min over x, min over y fxy problem, you would have to maintain decreasing function values along the path. And because the path is long, you need a lot of memory. So you cannot compute locally the function value. So the reason why min-max is harder than min, okay, so for min, you can find the local min, not the problem. The reason why you're not going to have to pay exponential complexity or number of queries, as I was talking about in the previous slide. The reason why min-max is harder than min-min is that min-max can implement this reduction from Sperner with only local information about where in this exponentially large domain you're at. While the min, if you wanted to do a min-min implementation, you would need to telescope. You need to have a function that is monotonically decreasing in these long paths that are created by Sperner. And that cannot be a local computation. It would have to be a global computation, so the reduction would not be polynomial time reduction. So this is very, very, very rough intuition for what is taking place. So the point of this thing, of this discussion, was that finding GDA fixed points, which is a solution concept that always exists, it's PPAD complete. It's as hard as Brouwer and other problems in PPAD. So, which motivates that instead of targeting general functions f, we should look at problems that are important and have more structure into them. And one of these problems I claimed, which is a very fruitful frontier, not well understood, in which to explore, is the multi-agent reinforcement learning problem. So I'm not gonna, I have only a few minutes left, so I'm gonna go over it very fast, but I hope you're familiar with market decision processes where an agent chooses an action that influences the state of the world, and the state of and the action together with the state gives a reward to the agent, and the agent then adapts their action and so on and so forth. Right, so the notation is that, like the world is described by two functions, a probability distribution that samples the next state given the current state and the action of the agent, and it also samples a reward that depends on the state, the action, and the next state. The agent in here wants to come up with a policy which specifies a probability distribution over actions for every state of the world, and the goal of the agent is to maximize their long-term expected reward under the policy. So they want to find a policy that maximizes this function V of P. What is VP? It's an expectation of the reward that the agent will collect in the future if the starting state is sampled from some initial distribution, and then the actions are sampled by the policy chosen by the agent, and the next states are sampled according to the mechanics of the world. So this is a standard MDP problem, and there is a natural generalization of that that has been studied in the context of multi-agent reinforcement learning that goes back to Shapley, who defined stochastic games, and to Littman, who proposed looking at those games in the context of multi-agent RL. So in that world, you have many agents, not just one agent. The state of the world is influenced by, is sampled depending on the actions of all the agents. And the reward to agent I depends not only on the state and their own action, but also the actions of the other guys. Every agent has to come up with a policy that samples their own action given the state. And agent I's goal, okay, this is I's goal, is to find a policy that maximizes the reward. But the reward depends not on their own policy, but also the policy of the other people. So the reward is the long-term reward, expected reward. If you start a trajectory at the starting state and people choose their actions according to the policies, and the state of the world is sampled according to the mechanics that are driving the world. The point is that in this multi-agent world, you want to find Nash equilibria, which are collections of policies such that no agent can improve their payoff by switching their policy from PI to something else. Nash equilibria exist under mild conditions that basically correspond to roughly that the game stops in finite time with probability 1. And when n equals 1, when you have only one agent, this Nash equilibrium degenerates to an optimal policy for the MDP. Okay, so this is background. What is my point? My point is that there is lots of work on finding optimal policies in the MDP setting. Q-learning, policy iteration, policy gradient methods, and there's some exciting work, for example, these two papers that I'm citing here, in trying to understand the complexity and the sample complexity of computing optimal policies over here. I claim that the land is much more fertile here, I mean, more underexplored here in the multi-agent setting, where there are policy learning algorithms, but of course, in general, I mean, if it's a general game, it's at least as hard as finding Nash equilibria in stateless games, so it's PPAD hard. And typically, the algorithms proposed here are centralized. So you have a central optimizer that is controlling all the policies of all the agents and optimizing all of them together, which motivates the following thing. Look at two-player zero-sum two-player RL settings to escape the interactability coming from the general sum aspect, but also put an emphasis on decentralized algorithms. So the reason why this setting is actually very interesting is that min-max theorem actually holds. So if we're looking at the payoff to the second player in a zero-sum setting, min over P1, pi1, max over pi2 is equal to max min. So the theorem holds. But interestingly, this function is not convex-concave. So you have a situation where min-max equals max-min, as shown by Shapley, but the function is not convex-concave. So I feel like this is the right type of setting where you have lots of structure that enables the min-max theorem to hold, but the function is not convex-concave. So I think this is a very fertile ground to make some progress. In some ongoing work with Noah Golovic, who's my student, Dylan Foster, who's a postdoc at MIT, we show a gradient domination condition that implies that finding near stationary points implies finding equilibria, and we show that the 2-timescale policy gradient method converges in polynomial time and samples to min-max equilibrium. I didn't intend to give the details of that work, but I just wanted to mention that in the absence of extra structure, as we showed, the problem is PPAD complete, which motivates going after settings that have extra structure that may enable the computation of equilibria, even though the function involved are not convex-concave. So conclusions for my 2-part lecture. Min-max optimization and equilibrium computation are intimately related to the foundations of game theory, mathematical programming, and online learning. They have found profound applications in statistics, complexity theory, and many other fields. More recently, they have found profound applications in machine learning, which pose big challenges, which have to do with a high dimensionality and non-convexity of the problems, as well as the entanglement of decision-making and planning with learning about the environment. I expect these applications to explore in the future as machine learning turns to multi-agent learning applications, but also indirectly as machine learning models become more complex and harder to interpret, which motivates introducing learning agents to check the behavior of other learning agents, like what happens in GAN training, but more broadly, more broad settings of that flavor, or adversarial training. Thank you very much.
Thank you, Kostis, for this very exotic talk, I have to say. We were, I think, pretty amazed. I think there are some questions, but because we're a bit over time, I would suggest to answer them in the roundtable that we have in 20 minutes, more or less.
Yeah,
thank you once more. Mijang, do you want to have any comment about the social events that they're coming on the weekend, or do you want to close the session?
Yeah, so we have an announcement on the Mattermost platform. So where we basically said there are many exciting events planned by our volunteers. So please make sure you look through the events that are listed on our virtual MLSS webpage and join some of them and have a lot of fun. Yeah.
Okay, let's thank our speaker again. Thank you very much, Kostis, and see you in 20 minutes.
Thanks, everybody. Yeah, thanks for staying.